Thanks to the organizers for the invitation. So the title of my talk is root numbers and parity of local Iwasawa invariants. So in my talk I will define this Iwasawa invariants, and so these invariants, they are integers, and here parity means whether they are even or odd. So this parity will help us in understanding. So we consider this family of elliptic curves E1. So I will define what this means. So I will consider elliptic curves which have this property that they are p-torsion points, they are isomorphic as Galois modules. And from this parity of local Iwasawa invariants, if you have information about the rank of one of the elliptic curve, you can say something about the rank of the other elliptic curve. And also you can, if you know the root number of one of them, you can say something about the other. So that's the idea. So let's start with some basics. I seen you have seen all these things in the last week quite a couple of times. So since I will be mainly considering elliptic curves over the rational, so it's given by this equation y square equal to x cube plus ax plus b, where the coefficients, they are coming from rational numbers. And you have to consider this extra point at infinity, and the discriminant of this equation should be is not equal to 0. That means it has distinct roots. So geometrically it ensures that we have tangent at each point of this elliptic curve. So now this is a well-known theorem that if you consider an elliptic curve over number field, now we can define an operation on this, on the set of points on the elliptic curve, and then it will form an abelian group. Now over Q, model proved that this is finitely generated, which was extended to number fields by Andre Weil. And now if you use the structure theorem of finitely generated abelian groups, then you see that Ek is isomorphic to z to the power r cross t, where t is a finite group. Now this we call R the rank of E over K, and T is the torsion subgroup of E over K. So till now we know something about this torsion part. For example, if you consider elliptic curves over rational numbers, then we have Mazur's theorem, which says that there can only be 15 groups which can occur as the torsion subgroup. We also know if the degree of K is 2, that means if you go to quadratic fields, then also we have complete information about this torsion part. There are some 26 subgroups which can occur as the torsion subgroup. But for greater than equal to 3, there are some partial results known. So this R is the mysterious part, and Iwasawa theory somehow helps us in understanding this R. So now we come to the torsion points, the n torsion points on elliptic curve, and they form a Galois module. So let E over Q be an elliptic curve, and you take n greater than equal to 2 be an integer. Then if you look over Q bar, then that forms, so that is isomorphic to 2 copies of Z mod nz. Now consider the absolute Galois group, G Q bar over Q, and now this acts. See, this Galois group acts on the elliptic curve. So if you take sigma and P is a point on the elliptic curve, then sigma P will also be a point on the elliptic curve, because sigma fixes Q and the coefficients are coming from Q. So not only it acts on the elliptic curve, it also acts on the n torsion points. So if you have np equal to O and this np sigma, it will be same as this. So this requires a proof, a little bit of checking. So you can find it in the book of Silverman and Tate. It is given there. So we thus obtain a modern Galois representation, this rho bar. So since this is 2 copies of Z mod nz, so you land in GL2 Z mod nz, where the lateral isomorphism involves choosing a basis for En. So you have this modern Galois representation corresponding to this elliptic curve. So this Iwasawa theory, it is a study of ZP extension of fields, where ZP denotes the set of p-adic integers. So if f over k is a ZP extension, Galois theory shows that for each integer n greater than or equal to 0, there is a unique intermediate field such that the Galois group of Kn over K, that is isomorphic to Z mod P and Z, and F is basically the union of all these intermediate fields. So now write gamma is Galois group of F over K, and the beautiful part about that, this lambda, this gamma, this ZP, this lambda is equal to ZP gamma, this is isomorphic to this power series ring in one variable. So, and these are very nice rings. And as Sujata was saying that we are going to a very large extension, but this, since lambda is isomorphic to this ZPT, we can use some nice structure theorem of this module, any gamma modules. So two lambda modules M and N, they are said to be pseudo-isomorphic if there is a homomorphism M to N with finite kernel and co-kernel. So if they are isomorphic, then kernel and co-kernel should be equal to 0, but here pseudo-isomorphic means we can allow them to be finite. Now as I was saying, so if you take any finitely generated gamma module, then M is basically pseudo-isomorphic to this. So we have this nice structure theorem, for example, as modules over PID. Here also we have this nice structure theorem that M should be, but here it is not isomorphic, it is pseudo-isomorphic. So M is pseudo-isomorphic to lambda R, and this, where they are integers and this is distinguished. So distinguished means this polynomial is monic and the rest of the coefficients, they are divisible by P. So, and this decomposition is also unique up to the ordering of the factors. So next we come to the Selmer group. So you take number field K, now V runs over all primes of K, Archimedean and non-Archimedean. So Archimedean here means infinite primes. And so if the degree is finite, then Kv is the completion of K at V. Otherwise we take Kv to be the union of the completions at all finite extensions of Q contained in K. Then you have also seen this in the last week, that Selmer group is defined by as the kernel of this map from H1K torsion here. And this state Shafarevich group, you don't have torsion here, you have the full EK bar. And the P primary subgroup of cell E over K is given by, so you don't take torsion, the full torsion, you take only the P primary part. So one can also show that the P primary part of this is basically this thing. So one can also show that. Now this Selmer and Tate-Shafarevich groups, they are important because they fit into this following short exact sequence given by this. Now suppose this rank of E over K is R, so you can write Ek as Z to the power R cross T, and when you tensor this with Q mod Z, this T tensor Q mod Z vanishes, so you only have Q mod ZR. So now if we assume that, which is a conjecture, that this psi is finite, and you know this, if you know about the structure of Selmer group, then you can say something about this rank of, anyway you can see that this Selmer group is an upper bound, this structure of Selmer group gives you an upper bound on the rank of E over K. So that's why this Selmer and Tate-Shafarevich groups, they are very important. So now choose P prime where E has good ordinary reduction. So you have heard these terms good and ordinary in the last week. So now ZP is the same p-adic integers, and cyclotomic is the cyclotomic ZP extension. That means Galois group of Q cyclotomic over Q, that is isomorphic to ZP. So now if you take this Pontryagin dual, that homomorphism of these two QP mod ZP, and if we denote that by X, then one can prove that this is a finitely generated gamma module. I think this was proved by Sudhanshu. Now this torsion part is difficult, and it was proved by Kato and some other. So now if we use this classification of finitely generated lambda modules, then one has a pseudo isomorphism that X is basically, so since this is torsion, you don't have the free part, you only have this torsion thing. Now this AI and mu JE, they are all positive integers. So one can have this lambda and mu, so they are given by this AI. So this lambda and mu, they are also positive integers. And this lambda E, we call this is lambda invariant, and this mu is the mu invariant corresponding to the elliptic curve. So next we define, we assume something that consider two elliptic curves EI defined over Q with good and ordinary reduction at P. So Ni is the conductor of EI over F. Now there is a notion of also conductor of EIP, and you take that, so that is also an integer, you take the prime part, prime to P part, so that is Ni bar. Now we consider sigma, this is the finite set of primes containing the primes of bad reduction of E1 and E2, the infinite primes and the primes above P. Now you make a new set sigma naught out of sigma, which V belongs to this such that V divides this. So I will tell why do we need these things. And this ACI is this V sigma naught such that EI has split multiple reduction at V, and this is the rank of this contragent dual of this cell P. So you have F here, and you have this F cyclotomic here. So this small SPEIF, that is for the base field, when this rank of the contragent dual of the base, and at the top that is given by that lambda invariant. So once you have these things, this is a nice theorem by Sudhanshu. He says that if you take E1 and E2 two elliptic curves, and such that these are some extra conditions, that E1P is an irreducible Galois bar over F module, and F contains mu P, so mu P should be contained inside F, and this C is finite. So finite, this is required because once you have this is finite, then you have this contragent dual of this will be finitely generated, and also not only finitely generated, it will be a torsion. So this condition ensures that fact. Then if E1P is congruent to E2P as Galois Q bar over Q modules, then you have this nice theorem. And if you just look at this ACI, this is a very small set, because the sigma, it is a small set, and now you are making sigma naught out of sigma. So one can check this thing. Now this Shekhar's theorem along with this P parity conjecture. So this P parity conjecture says that SPEF is basically congruent AEF mod 2. So they have the same parity, while AEF denotes the order of 0 of the Hasse-Weil function at is equal to 1. Now by BSD conjecture, this AEF is same as the rank of the elliptic curve. So then you can replace this SPE1F by the rank of the elliptic curve. So using BSD, this equation boils down to the fact that rank of E1F plus AC1 is congruent to rank of E2F plus AC2 mod 2. So once you know this AC1, AC2 and information about one of the elliptic curves on the rank, you can say something about the rank of the other elliptic curve. So this is important if it turns out that SPE1F plus AC1 minus AC2 that's odd. Then you can say that rank of the other elliptic curve is at least odd, it is at least 1. So, which is otherwise difficult to say to create a point of infinite order. So if you look at this theorem, there are two places where one can improve upon that. Suppose mu P is not inside F, then what will happen to this equation? And also if you don't have this ordinary thing, if you have supersingular, so with good and supersingular reduction and mu P is not inside. So these are the two places where one can improve upon, and basically we three worked on that, and we had some results in The first thing that we, okay, so now I will give a sketch of how the sketch of the proof. So for that one.
Parity conjecture, will it follow from the Iwasawa but you on the analytic side?
Yeah, all right. So first I will give the sketch of the proof how he.
Will be working with a function.
Yeah. So for this, we need this imprimitive Selmer group. So we take sigma naught as sigma minus the primes above p and the infinite primes. And so if you look at the Selmer, so we take this cell imprimitive as L belongs to sigma minus sigma naught. Okay. And under these two assumptions A and C, one can prove that basically lambda of E1 sigma naught is same as the lambda invariant for these two elliptic curves, this imperative Selmer group, they will be same. Okay. So for a prime V not dividing P, let this tau V1 denote the ZP rank of this Pontryagin dual of W dividing V. So basically what we are trying to do is, since we have, see this imperative Selmer group contains this usual Selmer group. So what we are trying to do is this, if we know that lambda E1 sigma naught will be same as lambda E2 sigma naught, but since it is bigger, we have to add some factors, and these factors are coming from this V belongs to sigma naught, and this sigma naught is what we have left out. So this lemma from this lemma where he proves that, so what he does is, yeah, so you have this sigma EIW, right? So the idea is that you have V here and you have this W1, W2, you have WIs here. So the first thing that we proved is that this sigma, so let us consider E1 first. So sigma E1 W is equal to sigma E1 W1. So let E is as E1. So one can show that this sigma, this corank of at each of the prime, they are same. Now since we are in a P extension, the number of primes is odd. So this tau is basically some S V times sigma W. So they are same for each of them, and this SV is basically odd. So from there one can say that this tau and this sigma W, they have the same parity. So this was the idea. So we prove that sigma E is at each of the primes above V, they are same. Now since there are odd number of these primes, the tau and sigma, they basically have the same parity. So you have this tau, all this tau coming up here. This tau is coming up because we have left out this sigma naught, and this is a bigger one, so you have to add this back. And then we prove that this tau and sigma W, they have the same parity. And so from here this follows. So now since this lambda E1 sigma naught is same as lambda E2 sigma naught, you can say that lambda E1 plus summation of the sigma E1 W is same as this. So next part is we have to compare the sigma E1 W, the parity of this. So that I will say later. So from these comparisons, so in Sudhanshu's case, since he had mu p inside, he could compute that explicitly, that for good this sigma, if E1W will be even, and for split, non-split, additive case, that will be 0. But if you don't have mu p inside that, then there are examples that is also given in his paper, for which in the good case you can have odd, and also in the split case you can have 0. So you don't have parity once you exclude that mu p is not inside F. So you cannot compute them explicitly. So anyway, so from that parity he can say that only since the split primes they have corank 1, so only they come up in this equation. So from the comparisons of sigma EIW, this lambda E1 plus AC1 is same. So this parity is coming up from that. The fact that it has split, it has odd, sigma E1 W odd, and rest of the cases it is even. So whatever we did, that was for this cyclotomic case. This, if we go to this F cyclotomy, now somehow we have to come down to the base, and this theorem of Guo, it tells us that if you have an elliptic curve defined over F, and this Contra-Gene dual of this is lambda torsion, then you have this theorem that SPEF is lambda E mod 2. So once you have this, then you can put SPEF on this. So you have the result that we wanted to show. So next we come to the case where mu p is not inside F. So then for p equal to 3, we have these following counterexamples. So you see that E1 has split multiplicative reduction, E2 has additive reduction. So, but both have rank 0. So on one part it is 1, the other it is additive, so it is 0, and so the equation does not hold. And also is another example where it has non-split multiplicative reduction and additive reduction, and same thing is happening. So what we noticed is that it is happening only for p equal to 3, that if one of them has multiplicative reduction and other has additive reduction, then that equation does not hold. So we have this main theorem. Here the conditions are same as him. We don't have mu p here, but we have this t coming up here. That t denotes the set of primes such that mu p is not inside Fv, and one of the elliptic curves has multiplicative reduction and other has additive reduction. So basically we looked at those examples and we found out that this is happening, and then we proved this thing. So note that t can be non-empty only when p equal to 3. So I have also that proof in the slide why this thing will be there. So in our case, so the idea was that since mu p is not inside F, you cannot compute that sigma EI explicitly, but at least you can compare them. So if they have the same parity, then we had this equation. So the other thing was this supersingular elliptic curves. So for n greater than equal to 0, we define this cell plus minus PE of Fn to be the kernel of this, where so for cyclotomic we take the direct limit of all the finite extensions, and we have these two special groups, because the fact is that the usual Selmer group is not lambda cotorsion. So that's why we need, so this is due to Kobayashi. We have these special groups coming up here, and then this will be a lambda cotorsion. Now if you just look at this, so this starts from -1 and this starts from 0. So F minus 1V is basically Fv, and so for n equal to 0 we have E minus Fv is same as E Fv, and cell P minus EF is same as E over F. Now this is the same kind of assumptions that we had made last time, that EP is an irreducible module and finite. So over Q, this is a result due to Serre, conjecture due to Perrin-Roux. So over Q. So then we have this theorem that E1, E2, two elliptic curves. This AP, we need that equal to 0, because the Kobayashi assumes AP equal to 0 in order to prove that for supersingular case the Contra-Gene dual should be torsion, and he uses AP equal to 0 in his assumption. So we have also that thing in our assumption. And this extra thing comes up here, that P splits completely over F, because we have a lot of local results. So if we have this condition, then FV is same as QP. So we will be using some results due to Kim, and Kim has results over QP. So we thought of extending those results, but anyway, right now we thought let it make it over QP only. So that's why we have this thing. Then we have the same kind of parity result here. If is a number field. If is any number. So the one thing that we had to do is that, so this was the first, when we thought of the problem, this was the first thing in our mind, that we need to have some equivalent theorem for GUO in supersingular case. That if you have this Ebian elliptic curve with good supersingular reduction and it is cotorsion, then you have to come down from the top to the below. So this was the first thing that we did, whether this, and this is, so GUO has done something for abelian varieties, and he used some divisible group, and that was used to construct a pairing which is non-symmetric and symmetric and non-degenerate. So for elliptic curves we had that pairing from Weil pairing, and so some results some things he was using, and those things we had also for elliptic curves. So we were able to generalize this theorem. So once you have this, then if you look at I said that cell P minus E over F is basically cell PE over F. So from that remark it follows that SPE over F lambda E minus. So we don't have plus here because you don't know what is cell plus PE over F. If you look at the definition, then you don't have plus coming up here. So we are only dealing with minus here. Yeah, so there is a hard, but that is only over Q. So yeah, formula is different. So Hartley, when we are working on that problem, so there is another guy, Hartley. He came up with a slightly different problem, but his problem was his result was only for E over Q. But we have this result over number fields. So this was the theorem that Sudhanshu used to calculate explicitly that sigma EI in W. So you can see that this P not equal to L be prime numbers and K finite. So see, this small k contains mu P. And you attach all the P power roots of unity to, and this is K infinity, then you have this theorem. So if E has non-split and additive, then this is finite, or for P greater than or equal to 5, this is 0. So you have this kind of results, and this was used to calculate the sigma EIW. But in our case, as he had counterexamples to that fact that if you don't have mu P inside, then you cannot compute them. Sometimes it is 1, sometimes it is 0. But the idea was that even if you cannot compute explicitly, then, but still we can say whether they're equivalent. So we can compare them. So one of the examples is this, that you take a finite prime of f v not dividing p, and this. So if E1 is congruent, E1p is congruent to E2p, then there has to be same. So the proof is here. So you consider this multiplication by p map, so you have AP. Now you have this long exact cohomology sequence. If you just write down that with respect to this G, you have this short exact sequence. Now for good reduction, you can find it in this theory of elliptic curves by Greenberg. So this H0 is divisible. Since H0 is divisible, this will vanish. So we have H1 GEP is isomorphic to H1 GEP infinity P. So you can put P inside. Now for any reduction, H1 G infinity, this is always divisible. So corank of this is same as, ZP corank of this is same as FP dimension of this. Now since E1P is congruent to E2P, so their dimensions will be same. So we have sigma E1W is equal to sigma E2W. So this is an example where even if you cannot compute explicitly sigma E1, still you can compare them once you have these informations. So this is one example. I won't give the proof here. The paper is on the archive, you can find it there and with all the details. So it says that it is not possible to have elliptic curves such that E1 has good reduction and E2 has additive reduction with this thing. So basically this good reduction, this will tell you that E1P, this E2P should have some torsion point, but since E2 has additive reduction, it cannot have. So from that contradiction, one can prove that this is not possible. So next I will tell that why for P greater than equal to 5 it is not possible. So this is one of Diamond Taylor's paper. They have this result that if you have multiplicative reduction and if you consider this unique non-trivial unramified quadratic character, for non-split case you have delta, and for split case this delta is trivial. And so if you so we'll mostly be working with this because we are in EP case. So we have, so for non-split case this delta will be there, otherwise for split case you don't have delta here, you only have this representation. So we use this representation to say something about this. So let P greater than equal to 5 be a prime and V be a finite prime with V not dividing P, then it is not possible to have elliptic curves with such reduction types. So, so suppose E1, so we only consider this case split, non-split can be proved also, the proof is given there for non-split case. So suppose E1 has split multiplicative reduction at V, now you just attach mu P to this FV. Now this F bar is unramified outside P, so the reduction type won't change.
As Galois.
Yeah, as Galois modules. So since F dash is unramified outside P, the reduction at V does not change for E1 and E2 over F bar. So from Hachimura's Matsuno's theorem, we have that E2P infinity, if you attach all the P power roots of infinity, so it has no, E2P infinity there is 0. Hence P part is also 0. So this is inside FV mu P infinity. So this cyclotomic is inside that whole, this is a bigger field. So inside that it will be equal to 0. Now, if you look at the representation, their rho bar will be equal to this 1. So since mu P is inside, this is 1. So you have this 1, 0, psi 1.
V divides P, right? Oh, V does not do.
Yeah. So but from this, if you look at this representation, you have this E1 should have some P torsion, which is a contradiction to the fact that E1P is congruent to E2P. Hence it is not possible to have elliptic curves E1 and E2 with such reduction type. So here we prove that E2P is 0, but looking at the representation we have E1P is not equal to 0. So this is a contradiction to the fact that they are isomorphic as Galois modules. So next we come to this root number part. So E over Q be an elliptic curve of conductor N. So you have this L function attached to E, where so these are for the primes of good reduction. So for bad reduction you have this 1 minus T, 1 plus T, those Euler factors, they will come up here. So now consider this gamma ES this, then by the modularity theorem, it's analytical continuation, you have this functional equation. By this WE, this is the root number, it can be plus minus 1. So what we proved is that if you have E1 and E2 be two elliptic curves defined over Q with good reduction at an odd prime P, and this E1P is congruent to E2P, then you have WE1F, WE2F is minus 1 to the power this thing. So this we proved this. Now if you use this our theorem, this under the assumptions of main theorem 1 or main theorem 2, you have minus 1 SP E1F, SP E2F. So we proved that if you just plug in this SP E2 there, so you get WE1F is this thing. So this is another version of this P parity conjecture, which states that WE over F is basically minus 1 SPEF. So this is another version of, it follows from the Hasse-Weil conjecture and the BSD. Yeah, I can show that. Now if you look at this corollary, you will find that if the P parity conjecture is true for one of the elliptic curves, then it is also true for the other elliptic curve. So I'll just say something about the motivation of our paper, that, so this is, if you have E over F, now if you look at all the, P torsion points of E as Galois F bar over F module, then Faltings proved that looking at all these P torsion points, you can say something about the rank, you can say about the rank of the elliptic curve E. So the idea is that if you don't have EP infinity, so Greenberg and Butzel, they used EP. So they considered EP and they tried to understand the different invariants. For example, this cyclotomic Iwasawa and algebraic and analytic invariants, they studied the difference in that case. They also, for example, they gave a formula for the lambda invariant, precise formula. If you have two elliptic curves, E1, EP, E2P, they are congruent, then how the lambda invariant changes. So all this work was inspired by that Greenberg and Butzel's paper, where they studied this difference of Iwasawa invariants. So what we thought was that what happens to the rank of the elliptic curves in this family? What can you tell? Even if you cannot compute, if you can say something about the rank of one of the elliptic curves from the other. So that was our whole idea.